Good morning. I'm Jeff Tsao from Sandia National Labs in Albuquerque, New Mexico. I've been a researcher in physical sciences and engineering for most of my career, working on semiconductor materials and devices like this blue light-emitting diode on the left. For the past 10 years, though, since 2013, I've been deeply engaged in meta-research, research into how human intelligences do scientific and engineering research. This book on the right, The Genesis of Technoscientific Revolutions, published in 2021 with my co-author Venki Narayanamurthy, is one of the results. On a separate front, there has also been, as we all know, amazing progress made this past decade in artificial intelligence, with new applications emerging daily. One of these applications is AI for science and engineering, as exemplified by this AI for Science Department of Energy report. So a natural question to ask is, can we build on what we have learned about how human intelligences do research to enable artificial intelligences to do research? I think so, but it's important to recognize that artificial intelligences doing research is not the same as simply AI for science. Research, at least at the extreme of knowledge exploration, is a creative act. It does not follow logically and rationally from what we know. The blue LED I just mentioned is an exemplar of this. The impact of the blue LED has been huge. Its discovery was awarded the 2014 Nobel Prize in Physics, and it has enabled a revolution in lighting efficiency with an estimated decrease, when it's all said and done, of 3 to 4% of primary world energy consumption. But the backstory, less well known, is that in order to make their discovery, the winners of the Nobel Prize had to go completely against common wisdom, toiling in obscurity for many years, even laughed at by many of their colleagues before they succeeded. As we have seen countless times in the history of science and engineering, the common wisdom of a society of agents, in this case human agents, is provisional and sometimes false. The essence of creativity in science and engineering is the overturning of that provisional knowledge by individual agents who see and think differently from the society they are embedded in. So today I'd like to sketch our emerging perspective on creativity in science and engineering, using human agents as a starting point, but with artificial agents very much in mind. First, I'll give an overview of what we call the technoscientific method. This is basically a new framing of all the steps that human intelligences do as they advance science and technology. Second, I'll give our working definition of creative outcome in science and engineering. Third, I'll discuss surprise, a pivotal piece of creative outcome, and how that surprise is mediated by multi-agent coopetition. Fourth, and finally, I'll discuss a key, though speculative, emerging insight on that coopetition, that it depends critically on two kinds of knowledge representations, the neuro and the symbolic. And before we dive in, a quick heads up. I do like to spend quite a bit of time on my slides, so it may seem like I'm going pretty slowly, but I actually don't have very many slides. Okay, let's start with the technoscientific method. Many of the ideas on this slide were newly proposed in Venki and my book, but I think you will find the ideas to be reasonable, in hindsight, almost obvious. There are two main ideas. The first main idea is that there are two repositories of technoscientific knowledge, science and technology. The science repository, S, in uppercase and in blue on the left, has two bins, both of which will probably be familiar to you: facts and explanations of those facts. The technology repository, T, in uppercase and in green on the right, also has two bins: human desired functions and forms that fulfill those functions. Note that this is a brand new formulation. Previously, technology has been largely thought to be forms, with functions considered to be outside of technology. If you believe that, then you believe that an engineering researcher's job is to take functions as given and simply to create forms to fulfill those functions. This can, of course, be exceedingly difficult, so I by no means mean to denigrate it, but it is only half of an engineering researcher's job. The other half is to find functions that humans desire, and this is at least as, if not more, difficult. Thus, in our formulation, technology consists of both forms and the functions they fulfill, and the repositories of scientific and technological knowledge become elegantly symmetric. Just as in science, explanations exist to explain facts, in technology, forms exist to fulfill functions. The second main idea is that the evolution of these two repositories of knowledge is mediated by what we call the technoscientific method, a new phrase that represents the interacting combination of a scientific method, what we call S dot, and an engineering method, what we call T dot. Note that this is also a brand new formulation. We are making a crucial distinction between the nouns of science and technology, their repositories, S and T, and the verbs of science and technology, the methods by which they advance, S dot and T dot. Said differently, there is a big difference between a scientist, someone who knows a lot of science, and a scientific researcher, someone who is advancing science. Likewise, there is a big difference between an engineer, someone who knows a lot of technology, and an engineering researcher, someone who is advancing technology. I won't go into detail, but let me give you a brief flavor for the scientific and engineering methods. The scientific method in lowercase and in blue on the left starts with the finding of facts. With facts in hand, the method proceeds to the finding of explanations for those facts. And then, with emerging explanations in hand, the method proceeds to the generalizing of those explanations to predict possible new facts, triggering a hunt for those new facts. The engineering method in lowercase and in green on the right is analogous to the scientific method. The method starts with the finding of human desired functions. Then, with functions in hand, the method proceeds to the finding of forms that fulfill those functions. This brings us to the third leg, the co-opting of existing forms to fulfill functions they were not originally intended to fulfill. This we call exapting, a word borrowed from evolutionary biology, in which biological forms like dinosaur feathers, which originally fulfilled the function of thermoregulation, are co-opted for other functions, like flight. Before we move on, let me make one overarching point that we believe this technoscientific method, as practiced by human intelligences to advance science and technology, is complete. Every mechanism is necessary, and there are no additional mechanisms. That means if we want to build artificial intelligences that also advance science and technology, we know the mechanisms we need to build into those artificial intelligences. The mechanisms are not mysterious. As advertised in the title of this talk, though, we are not interested in just any kind of scientific and engineering advance. We are interested in creative advance. So let's turn now to creative outcome in science and engineering. Here we make use of two ansatzes, two basic assumptions. The first ansatz is what I call the evolutionary ansatz, that creativity serves an evolutionary purpose. In the exploration and exploitation processes that evolutionary adaptive systems use to produce and employ useful knowledge about their environments, creative outcome is successful exploration, hence significant advance in that useful knowledge. Creative outcome is useful learning. The second ansatz I call the Simonton ansatz, after Dean Simonton, that we might express useful learning as the product of utility and learning, U.L. Creative outcome can only be high if both utility and learning are high. If either is low, then creative outcome is low. Now let's make this more concrete using the diagram at the bottom right. Suppose we have a potential nugget of knowledge and we make guesses as to its utility. Along the left axis of this rightmost graphic, in red, I plot our best guess before the potential nugget of knowledge is tested. Along the right axis, in blue, I plot our best guess after the potential nugget of knowledge has been tested. In this particular scenario, I've drawn a prior probability distribution that is broad and at the lower end of the utility scale, and a posterior probability distribution that is narrower and at the higher end of the utility scale. This means that after testing, we've learned. We've learned that the potential new nugget of knowledge is more useful than we originally thought, and we are less uncertain about that usefulness. To measure how much we've learned, we use the so-called Kullback-Leibler KL divergence, a standard measure of the information gained when a prior is updated to a posterior probability distribution. I won't go through the math, but we'll just say that how much one has learned ends up depending on two key characteristics of the two distributions. Delta B is what we call blindness reduction. It's basically the change in the width of the distributions. S is what we call surprise. It's basically the change in the mean values of the two distributions. As it turns out, the dependence of learning on surprise is much greater than the dependence on blindness reduction. It ends up going as the square of surprise. And because surprise is what we might call implausibility, we can think of useful learning as being implausible utility. And that's exactly the scenario drawn here. The potential new nugget of knowledge was thought not to be useful. Its utility was disbelieved, but it turns out to be useful. That disbelief was disconfirmed. The potential nugget of knowledge has implausible utility and is thus an example of creative outcome. Note there are two things that creative outcome is not. The first thing that creative outcome is not is more certain utility. It doesn't mean blindness reduction, though blindness reduction does have a role in knowledge advance. It's just a very different role than that of creative outcome. I liken it to this graphic here in the middle. The evolution of biological life is described by punctuated equilibria, in which species, for the most part, adapt to their environment as time goes on. That's meant to be conveyed by the thickening of these lines as time advances upwards. But every once in a while, there are sideways breaks where completely new species are created. In the case of knowledge evolution, there is also the extension and consolidation of existing knowledge in which blindness is reduced. And there is also the punctuation by sideways breaks as existing knowledge is surprised. I would say this is actually the single most difficult notion for even working scientific and engineering researchers to get. There is nothing wrong with blindness reduction, but if they are after creative outcome, it is surprise they must aim for. The second thing that creative outcome is not is novel utility. Novelty is often thought to be one of the criteria of creative outcome. In this formulation, novelty is not necessary for creative outcome. It's surprise that is necessary. Novelty might be a good leading indicator of surprise, but that's all it is. You can have novelty that isn't surprising, like a never before seen license plate number that doesn't overturn any previous knowledge. But you can also have surprise that isn't novel, like the observations of Neptune that had been under astronomers' noses for centuries before they were suddenly taken seriously as a possible new planet. Okay, so surprise is what one is looking for in creative outcome. But surprise to whom? Is it surprise to the individual doing the research? Or is it surprise to common wisdom, to expert peers in the knowledge domain the individual is working in? In scientific and engineering research, of course, it's the latter. Common expert wisdom is ultimately what is cumulative, what society passes on from one generation to the next. So we're talking about big C creativity, surprise to society, not little c creativity, surprise to the individual researcher. But what about the latter? Does surprise to common wisdom imply surprise to the individual? No, it doesn't. To see why not, I've drawn a diagram with two axes. The bottom axis is what common wisdom thinks the utility of the potential new nugget of knowledge might be. The left axis is what the individual researcher thinks the utility of the potential new nugget of knowledge might be. On the diagram is depicted two possibilities. At one extreme is possibility A, in which common wisdom thinks the utility will be high, as does the researcher. In this possibility, there's not much opportunity for surprise. Even if the researcher is right that this potential nugget of knowledge will be useful, it won't be surprising to common wisdom because common wisdom already thinks it will be useful. At the other extreme is possibility B, in which common wisdom thinks the utility will be low, but the researcher disagrees and thinks it will be high. This is where there is opportunity for surprise. It is precisely when the researcher disagrees with common wisdom that there is opportunity for surprise to common wisdom. Why might the researcher disagree? It might be because the researcher has some inside knowledge that gives him or her an unfair advantage over common wisdom. Maybe the researcher has a new tool, like Galileo's telescope, that enabled him to see the moons of Jupiter and thereby overturn Earth exceptionalism. Or maybe the researcher has thought through the problem more deeply, down to first principles, like Einstein's deep thinking leading to the theory of special relativity and thereby overturning the belief in the independence of time and space. Maybe the researcher has insight into human nature that, like Steve Jobs, enabled him to see the human desired functionality of iPhones, even at $500 per phone, that few others could. Or maybe the researcher has insight into related knowledge domains, like bicycles, enabling the Wright brothers to disprove the impossibility of heavier than air flight. In other words, it is when the researcher is not just a contrarian, but an informed contrarian, where there is the most opportunity for surprise. Any researcher can be a contrarian just to be a contrarian. But not just any researcher can be an informed contrarian, so deeply informed that there is a decent chance the researcher is right and common wisdom is wrong. The bottom line, opportunity for surprise is maximized when there is the greatest discrepancy between the researchers and common wisdom's common wisdom's guesses about utility. It is a bit like what Peter Thiel, the high-tech venture capitalist, says, tell me something that's true that almost nobody agrees with. Let me make one last point about big C creativity before we move on, that it depends on multi-agent coopetition. Coopetition is required because common wisdom must be rolled up from the knowledge of individual agents. But competition is also required as individual agents compete with each other to surprise that common wisdom. So a key question, one that we'll speculate on in the next slide, is how do human, much less artificial intelligences, do that? One possibility for how human intelligences do that, and for how artificial intelligences might do that, is that we make use of two different knowledge representations. One knowledge representation, illustrated in green on the left, is symbolic. It is what Michael Polanyi would call formal and logical. It is reductionist and explanatory. Most importantly, it is teachable from one agent to another, so is cumulative, even as individual agents are born and die. The other knowledge representation, illustrated in red on the right, is neuro. This is what Michael Polanyi would call tacit knowledge. It's the recognitional knowledge that enables us to holistically see either the young or old woman in this famous Gestalt sketch, but not both at the same time. It isn't teachable, and it isn't cumulative. However, because it is holistic, it allows us to see patterns and analogies across knowledge domains that we wouldn't see if we were limited to reductionist thinking within one knowledge domain. These analogies could be just hallucinations, of course, but they could also be breakthrough insights that lead to surprise. Switching from seeing the young woman to seeing the old woman could be just the aha that solves some puzzle at hand. For human intelligences, we could liken the neuro and symbolic knowledge representations to Daniel Kahneman's System 1 and System 2 think fast, think slow modes of thinking. Think slow is symbolic thinking. It's accurate, rational, but slow. Oftentimes, it's so slow that you have to use computers to do it. Even with computers, it can be too slow, and hence drives the Department of Energy, for example, to build its supercomputers for scientific computing. Think fast is instinctive thinking. It's inaccurate, irrational, but fast. It's why ChatGPT and other machine learning models can be so fast. Even if the neural network they are based on has hundreds of billions of parameters. Once the parameters are frozen, once the model has been trained, inference using the model is holistic and instant. No symbolic manipulation is required. If this is right, then we need both knowledge representations. Symbolic representations to enable us to accumulate knowledge and turn it into common wisdom, and neuro representations to enable us to surprise common wisdom. This also means we need to be able to translate back and forth between representations. On the one hand, we need to translate from the neuro to the symbolic. For artificial intelligences, this is known as explainable AI, where one tries to explain how it is that a machine learning model can distinguish cats from dogs. For human intelligences, we might call this explain the aha. It's not enough to have a sudden new insight. You have to represent the insight symbolically so that you can explain it to yourself and to others. On the other hand, we need to translate from the symbolic to the neuro. We might call this instinctivize the symbolic. I liken this to the following classroom experience that many of us have had. You're taking a STEM class, and you learn the symbols and equations and how to manipulate them so that you can do the problem sets. But you're still pretty mystified, so you keep thinking and thinking about it. Then, just when you've almost given up, you have an aha moment in which suddenly you understand what the symbols and equations are about. Finally, let me come full circle and connect back to the technoscientific method. In that language, cumulative science and technology, S&T, is symbolic and rational. It's basically Isaac Newton's, if I have seen further, it is by standing on the shoulders of giants. In contrast, advances in science and technology, S. and T. are neuro and intuitive. It's basically Albert Einstein's imagination is everything. It is the preview of life's coming attractions. Let me close now with a few takeaways. Takeaway 1 is that the technoscientific method isn't mysterious. It's just a series of steps that human agents do. there's no reason to believe that how human agents execute it shouldn't be translatable to how artificial agents might execute it. Takeaway 2 is that creative outcome in science and engineering also isn't mysterious. Its essence is surprise and implausible utility. Takeaway 3 is that implausible utility also isn't mysterious. It's basically a multi-agent coopetition game. Agents cooperate to create common wisdom while competing to surprise that common wisdom. Takeaway 4 is that one key to implementing that coopetition might be two different knowledge representations: the symbolic, to represent and accumulate common wisdom, and the neuro, for the imaginative analogical reasoning that surprises common wisdom. With that, thank you for your attention.